Welcome back, everyone, and welcome to Chapter 9. This week we're going to be talking about methods to control microbial growth, whereas in previous lectures recently we've been talking about how microbes grow in population. Now we're going to be talking about basically the opposite. How do we control them or prevent their growth in order to keep us healthy? So, controlling microorganisms, this is 9.1 from the text. We aim oftentimes in the medical community to control our degree of exposure to pathogens. That's a monumental concern for our lives because, of course, pathogens make us sick. So there's various methods that we can use that can help reduce or eliminate microbial growth from a surface or an instrument or in the body, on the body, etc. And so those four possible outcomes that can arise from these processes are listed here. There is sterilization, disinfection, decontamination, and antisepsis. Note that two of these at the bottom have additional terms that mean the same thing. So it's important for you guys, for your field as well as exam purposes, to understand the difference in these terminologies. So this table comes from your book, and basically what I've done is highlighted some important points and also kind of lumped everything in one table so we can compare and contrast them all on one slide. So our first term that we mentioned was sterilization. This process destroys or removes all microorganisms, including viruses. So there are no microbes that exist on or in whatever it is we're sterilizing after that sterilization process is complete. So sterile is not a term you use lightly. It should be used in a very strict sense to refer to materials and items that have been through a sterilization process. So this is commonly used for things like surgical instruments, anything that you would put in the body, especially syringes, even commercially packaged food goes through these processes to keep them from making people sick. So again, you should know the things especially that are highlighted. Sterilization destroys all microbes. There are none left. Disinfection, on the other hand, will destroy vegetative pathogens, but not bacterial endospores. So if you recall from a couple chapters back when we talked about bacteria and how some of them can form endospores, when they are in their non-endospore stage, those were called vegetative cells. That's where they're just doing their thing, they're living their life, and then whenever conditions get harsh, those vegetative pathogens can form endospores, and then that's where they stay dormant for a while until conditions become favorable again. So in the process of disinfection, we're destroying all the vegetative pathogens, but it does not eliminate bacterial endospores. Decontamination or sanitization is a method that is going to simply just reduce the amount of microbes to a safe level. So I can consume, for example, food, or I can use cooking utensils. I can use forks that have bacteria on them. Remember, bacteria are everywhere. And I'm not going to get sick from using a fork that was in the dishwasher 5 days ago, let's say. Does it have bacteria on it? Yes, but it's a low enough level that it's safe for me to eat off of. So decontamination or sanitization is simply just reducing the number of microbes to where it's a safe level for us to be able to use it. Lastly, we have antisepsis or degerming. This is similar to decontamination, but don't get them mixed up. This one reduces the number of microbes, but it's specific to living tissues like human skin, for example. You get a boo-boo, a sore or something, and you put alcohol on it, or hydrogen peroxide, for example. Those would be considered examples of antiseptics because they're reducing the number of microbial organisms on or in living tissues. Okay, so next we're going to talk about the various ways that we have to control microbes. There are physical agents, chemical agents, and mechanical agents or methods as shown in this table. So this table is really great because it kind of gives you a really broad overview of all the things that we'll discuss. So in physical agents, we'll talk about heat and how we use it as a microbial control method. We'll talk about dry methods, moist methods. We'll talk about radiation, the different types of radiation. We'll talk about various gases and liquids that are chemicals that we can use to disinfect or sterilize things, etc. And we'll also talk about filtration. So before we jump into that though, let's talk about the relative resistance of microbes. So what this picture is showing you here is that not all microbes have the same ability to be resistant from these various chemical, physical, or mechanical methods of microbial control. What it's showing you is the less resistant organisms at the bottom, and as we go up this chart, we're seeing more and more and more resistant bugs, we'll call them. I do sometimes call bacteria and virus and stuff just bugs as a general name, but as you can see, some things like our envelope viruses, they are more susceptible to our microbial control methods than, let's say, non-envelope viruses. So basically, again, this is showing you an order. Our envelope viruses are very unresistant to a lot of these things. So they're the easiest thing to kill. That's the important part here. What this also is showing you. Easiest to kill. And I'm going to write kill in quotations because this is a virus, so technically they're not alive. So maybe a better way to word it would have been easiest to inactivate. But any hoodle. Same here, except the opposite. These are the hardest to kill. And again, quotations, because technically prions are not a living thing. So it's going in increasing order as we go up. So the second hardest thing to kill is bacterial endospores. And that hopefully isn't a surprise, because remember in that chart we said sterilization was removal of everything. And then the next one that we talked about was disinfection. And it was able to kill vegetative cells, but not bacterial endospores. So that is our next hardest thing to kill. You should know this. Know that. Very hard to kill. Very resistant. And then we have next mycobacterium. We have staphylococcuses and pseudomonases. Those are just various genuses of bacteria. You don't need to know this whole order, but I would definitely know that bacterial endospores are really difficult to eliminate. I think also you should probably know that our gram-positive and gram-negative. So bacteria that are gram-positive, relatively easy to kill compared to gram-negatives. Gram-negatives are relatively, though, easy to kill compared to organisms that have endospores. Alright, this shows you some examples to, or it shows you some data to verify that information that we just covered. You do not need to memorize this. I'm clearly not very good at this with the pen. Okay, close enough. Anyway, so it talks about the various methods that, some of which we've mentioned, like heat and radiation, sterilizing gas, and some kind of sporicidal liquid, specifically 2% glyceraldehyde. And it shows you what the requirements would be for each one to destroy endospores compared to vegetative forms. So if we think about heat, that's the first one here. In order to kill vegetative cells, we only need to heat up to 80 degrees Celsius. And for reference, that is 176 degrees Fahrenheit. Not even boiling point. Comparatively, in order to destroy endospores, we would need to reach temperatures of 120 degrees Celsius. And for reference, that is 248 degrees Fahrenheit, well past boiling point. Boiling point is 212 degrees Fahrenheit, in case you're wondering, and 100 degrees Celsius. So essentially, bacterial endospores are 1.5 times more resistant to heat compared to vegetative cells. Now let's look at radiation. Radiation is measured in grays. If we compare the amount required to destroy vegetative cells to endospores, we can see we need a lot more radiation to kill endospores compared to vegetative forms. So, in fact, 4 times more. The ethylene oxide gas, you see the numbers here, 700 and 1200. 700 is for the vegetative cells. We need 1200 micrograms per liter in order to kill an endospore. So endospores are 1.7 times more resistant than vegetative cells when it comes to the sterilizing gas. And finally, if we look at the 2% glyceraldehyde sporicidal liquid, we can see that it will destroy vegetative forms in 10 minutes. It takes endospores to be killed, though, for 3 hours of exposure. So 18 times more resistant are the endospores compared to the vegetative cells with the sporicidal liquid. All in all, what the big idea here is that spores, and let me also write up here, bacterial, are hard to kill. And the reason why I wrote bacterial up here is I didn't want you to get confused with spores, meaning the type that we talked about when we described fungal reproduction. Okay, so that kind of spore is completely different than what we're talking about now. Alright, and maybe this will help you remember this too. My love for you is like an endospore, practically invincible. I thought it was a cute little meme, so I hope you like it. Okay, so now we're going to next talk about some generic terms, and I've listed them all on the same page because I wanted you to see the similarities. If you look at the following words, bactericide, fungicide, virucide, sporicide, germicide, or microbicide, all of them have a "cide" at the end, that CIDE, and that means kill, all right, to kill. So the root word bacteria is referring to bacteria. So it's a bacteria killer. It's a chemical that destroys bacteria, except for those that are in the endospore stage because they are a pain in the butt to kill. Fungicides are chemicals that can kill fungi. Virucides are chemicals that can inactivate or quote-unquote kill viruses. Sporicides are an agent that can destroy bacterial endospores. And germicides are chemical agents that kill microorganisms. It's more of a generic term. A couple other terms to be familiar with is sepsis and asepsis. Sepsis is the growth of microorganisms in the blood and other tissues. Definitely not a good thing. Asepsis is any practice that prevents the entry of pathogens into sterile tissues and thus prevents infection. And also, one more term, aseptic techniques is a practice that we use in healthcare that will ensure that we don't contaminate things that we don't intend to contaminate. So it can range from sterilization methods to antisepsis, but it's anything that we do to try to control this microbial growth. Antiseptics, another term, is a chemical agent that is applied to a body surface. So we've mentioned this one already. Actually, it was in that table, that first one I showed you. It's the one that was specific to being applied to living tissues. So some examples of this in the medical community or healthcare settings would be preparing the skin for surgery. So they typically are going to apply some sort of substance to the skin before they start making incisions, such as iodine. That will help to control microbial growth. Swabbing an open root canal with hydrogen peroxide would be another example of an antiseptic. No different than if it was just a wound on your hand or something and you poured alcohol or hydrogen peroxide on it. The fact that you are putting it on living tissue is what makes it an antiseptic. And ordinary hand washing with some kind of soap would also be considered an antiseptic. Couple more terms. Whenever there are terms that have a stasis or static at the end, it means quote unquote to stand still. So basically it prevents further growth from occurring, but it does not kill the microorganisms that are there. So a bacteriostatic is a chemical or some kind of methodology that's going to prevent the growth of bacteria, but not kill the ones that are there. So it prevents the growth. So make sure we know that distinction. Bactericide and bacteriostatic is not the same thing. A bactericide is an agent that kills bacteria, except for endospores, and a bacteriostatic stops their growth. Doesn't kill the ones that are there, but prevents them from making more. And likewise, a fungostatic is the same, except in applications to fungal growth. So it inhibits fungal growth without killing the fungus that exists. Alright, so next, the antiseptics and the drugs that have microbistatic effects, because the compounds can be toxic to cells. So antiseptics and drugs have microbistatic effects because the microbial compounds can be toxic. Alright, even a blank insert cytal at the end agent does not necessarily result in sterilization. It really depends on how it's used, how long it's been exposed to whatever it is being exposed to that it's intending to kill the bacteria on, etc. Alright, so let's kind of talk about this in practical matters when we're deciding how to clean or control the microbial growth from some kind of object or surface, etc. The things we need to take into consideration is, what is this thing going to be used for? So, for example, critical medical devices. These are things that must be sterilized before use. Like, they can't be decontaminated. They have to be sterilized. You do not want any type of bacteria growing or existing on a medical device that you're going to put in somebody's body. So, and for that reason, they must be sterilized. Some examples could be, let's say, a catheter, or not a catheter, excuse me, pacemaker, there we go. Or let's say breast implants or a hip replacement surgery. Those are all things that's going to have some kind of item being stuck inside the body, and we definitely do not want it to have any bacteria on it, because then it would grow in the body and that would lead to infection and not good. So those must be sterilized before use. Semi-critical devices is another category of medical devices that will come in contact with the mucosal membranes. Mucosal membranes are not sterile though, so disinfection and a high level of it is what you have to have for semi-critical devices, preferably sterilized, but they don't have to be sterilized. And then our non-critical devices are any kind of devices that don't touch the patient or only touch intact skin. So they don't really require much disinfection, just very low level disinfection, unless they become contaminated with some kind of blood or body fluid or any potentially infectious agent. So things in this category could be gloves, when you wear gloves in a lab. Alright, so that's just coming in contact with skin, or swabs for let's see, no, swabs wouldn't be sterilized. Let me backtrack. What else could be non-critical devices? A stethoscope, right? So we don't really, you don't sterilize those in between seeing patients. Might wipe it off, a little alcohol wipe or something. That's a non-critical device. Alright, so now that we've covered that, let's start talking about what exactly microbial death is. Because if you think about death in a person, it's pretty easy to determine when someone is alive or they are dead, because there are vital processes that have to be occurring in a organism in order for them to be considered alive. And for humans, let's say, death is the permanent termination of those vital processes. But when we're looking at a microbe, they don't really have any conspicuous vital processes. Like we can't see their heart beating, or they don't, can't talk to us or respond to stimuli that's very obvious that we can easily see. So it becomes more of a complication when we're trying to describe microbial death, because we can't, take a cell's blood pressure. They don't have that, of course, but I hope that you're seeing my point. It's just we can't really measure cell death for microbes the same way we would do for a entire organism. So what we measure cell death in terms of microbes is their permanent loss of reproductive capability. Permanent loss of reproductive capability. That is what we describe as microbial death. Microbial death. Permanent loss of reproductive capability. And you can probably guess that's going to be on the exam, because guess what? It's written in red and bold and so on. And I've said it several times now. Pay attention to things like that. All right. So our purpose in the healthcare setting is typically, like we said, to control microbes, so to kill them. So there are 4 general cellular targets that antimicrobial agents tackle. Some microbial agents will target the cell wall. If I have a bacterial cell and it has a cell wall and I attack it and break it down, it's going to kill that bacterium. Likewise, some bacterial antimicrobial or antibacterial agents will target the cell membrane. Some will target nucleic acid synthesis, and for the record, that is DNA or RNA. So not being able to produce DNA means that they can't do binary fission anymore. They can't make more bacterial cells if they can't make more DNA. And if they can't make RNA, they can't make proteins. So some biological metabolic compounds can be inhibited from being made also through some of these antimicrobial agents. So for example, some targets could be ribosomes. So these ribosomes make proteins. And again, if a cell can't make proteins, it's going to die. Sometimes the antimicrobial agents will attack the certain proteins themselves. If that protein is vital for life, then it's going to kill the bacterial host. Enzymes. Many enzymes are required for life. So basically, in this final category, these biological compounds are things that's keeping the cell alive. And so if we attack any of those things with this antimicrobial agent, it will kill the microbe. Okay, couple more definitions. The thermal death point and the thermal death time. So thermal death time is the shortest length of time required to kill microbes at a specified temperature. Whereas thermal death point is the lowest temperature required to kill all microbes in a sample in 10 minutes. And this is going to be relevant to know, especially for any kind of perishable substances, or if we don't want to heat up something too much to decontaminate it because it might cause it to spoil, or it might cause it to curdle, or it might cause it to melt, etc. So it'll help us determine how we're going to decontaminate something. So for example, if let's say I want to decontaminate or sterilize, whichever methodology, but I'm going to wind up needing to run, let's say, inoculation loops. They can come in plastic, which means they're disposable, but we still need to sterilize them. So the thermal death point would be the lowest temperature that we would need to sterilize that inoculation loop in 10 minutes. And we would want the lowest temperature possible, because if we have too high of a temperature, it might make the inoculation loop melt. So that would just be one example in reference to microbiology. So now what we're going to do is we're going to go through the chart of physical, chemical, and mechanical removal of microbes and the various agents we can use to do so. So first and foremost, we'll start with our physical agents, which are heat and radiation, but we're going to start with heat first. So heat is the most common method of microbial control, that is physical control. There are different types of heat, dry heat and moist heat. This slide is showing you examples of dry heat. Dry heat meaning water, is not involved. There's no liquid. So hot air, like an oven, or open flame. Open flame would be considered incineration, and that leads to sterilization. So if we look at the first bullet point in this indent, it talks about the oven. This is showing you a picture of a oven that would be found in a potential microbiology laboratory. But it can range in temperature from about 150 to 180 degrees Celsius and is a acceptable way to kill many microbes or even sterilize a substance or surface, etc. How does it do it? The heat is going to dehydrate the cell, and that removes water. All right, and water is necessary for life. So without water, it will cause the cell to die. It will also result in denaturation of proteins, which is basically where the heat is going to cause them to lose their shape. And so, as y'all should know, shape is related to function. If these proteins don't have the correct shape, they'll no longer be able to function, which will halt the cell's metabolism and ultimately kill it. And the time range is usually between 2 and 4 hours. Incineration involves an open flame, as seen here. We see someone that is sterilizing an inoculation loop, and another example here showing someone who is sterilizing the top of looks like an agar dish here. So what happens during incineration is we have very, very high temperatures that will oxidize the cells, and basically it burns them to ashes. And this results in instant death, instant sterilization, and the temperature ranges can be from 800 to 6,500 degrees Celsius. That is so hot, so hot. And then again, it's just showing you inoculation loops. I wanted to point that out specifically because we use those so often in the microbiology classroom and lab, and you should have seen them as well in your lab class. So moving to our next one is moist heat. Moist heat is basically steam under pressure, and the device that we use to do that is called an autoclave. So here you see a autoclave, and they're sticking some samples of something inside of it to be sterilized. This is basically like an Instapot. So I know that's a really common household small appliance. So for those of y'all that have one, what it does, as y'all know, if you've used one, you have to put some water at the bottom, and then when you turn it on, it has to reach pressure. So essentially, it's increasing in pressure inside of that Instapot. And then as that water heats up and is pressurized, now you have steam under pressure. So it uses that pressure to increase temperature past boiling point. So for reference, if you were just put water on the stove, not in the Instapot, just put it in a pot and put it on the stove, it will reach boiling point at 100 degrees Celsius. Or that would also be 212 degrees Fahrenheit. But if I put something in an Instapot or an autoclave, in the case of microbiology world, it's going to increase the temperature past boiling point, because not only is it heating it up, but it's also putting pressure on it. And so that is going to make us be able to push past boiling point to even higher temperatures. So at sea level, which is where we are, normal atmospheric pressure is about 15 pounds per square inch, or PSIs, or you can also say it's 1 atmosphere. At that pressure, water boils at what we know as boiling point, 100 degrees Celsius or 212, or 212 degrees Fahrenheit. But that's not high enough to kill all microbes. So in this autoclave, we're going to apply 15 additional pounds of pressure to this device, and it's going to result in a higher temperature than boiling point. In fact, it'll go up to typically 121 degrees Celsius. And after 15 minutes of that exposure to that temperature and pressure, it will reach sterilization. So you should know this. I have it in red for a reason and starring it, etc. So looking at this chart over here to the right, you'll see if we're adding 15 pounds per square inch of additional pressure to a system, it will reach 121 degrees Celsius, which is by far past boiling point. And it also shows you, some trends with this. So if we were to only add additional 5 pounds of pressure, it would reach 109. 10 pounds, 115 degrees Celsius. 15 pounds of pressure, 121 degrees Celsius. So the more pressure, basically the increase in pressure is going to result in a higher temperature. But this is the one that I want you to know, because this is how autoclaves are typically set up. This whole thing just shows the trend. This is the one I want you to know for the exam. Okay, so another method of moist heat is boiling water. So this is only disinfection, because again, it does not kill all cells. It will reach 100 degrees Celsius, boiling point for water, but it will not kill all cells. So it is disinfection and not sterilization. Next, pasteurization. This is disinfection, but it's specifically for beverages. So you may have heard of this term in regards to milk, for example, because milk is pasteurized. Many fruit juices, beer, and wine are as well. And what that is a technique where heat is applied to these various beverages to kill pathogens and other microorganisms that will prevent the item from spoiling. While at the same time, it doesn't heat it high enough to alter the flavor and the nutritional value of the beverage. So all in all, this process destroys about 97 to 99% of bacteria, but not all of them. So that's why if you were to buy milk and stick it in the fridge and never open it and wait a month and then open it, despite the fact that you hadn't opened it yet, it's still going to have spoiled because there are bacteria in that milk. Alright, so next let's talk about microbial susceptibility to heat specifically. Vegetative cells are equally susceptible to heat. Doesn't really matter what kind. However, if we have a cell that is currently in the endospore phase, then it's very resistant. Alright, so destruction of spores requires temperatures well past boiling point. Alright, so we would definitely need some kind of like autoclave or something to get rid of those. So again, vegetative cells, regardless if they're spore former or not, are equally susceptible to heat. Remember, just because a bacteria has the ability to form a spore doesn't mean it's always going to be in the spore state. So if it happens to be in the vegetative state, it will kill it using the heat methods of boiling. But if it's in the spore state, it will not. Pathogens are neither more nor less susceptible than non-pathogens. So basically, bacteria that don't make us sick are just as susceptible as ones that do. Fungi, protozoa, and worms are similar in their susceptibility to heat, and viruses are pretty resistant to heat. Their tolerance extends from 55 degrees Celsius to 2 to 5 minutes to 60 degrees Celsius for 600 minutes. So they're pretty resistant comparatively than other things to heat. What about cold? So on the other end of the spectrum, most microbes are not killed by being cold. We can refrigerate and even freeze microbes, and they will still be revivable if they are brought back to their temperatures that they like. So for example, if you were to ever go into a microbiology lab, it's not uncommon where they'll have freezers that will reach temperatures as low as -70 to even -135 degrees Celsius. That's extremely cold. But we can use these frigid temperatures to preserve cultures of bacteria, viruses, or even fungi for very long periods of time. In fact, so in my lab on campus, I have cultures of various bacteria that I keep in the fridge. and they don't grow anymore because they're in a cool temperature. But if I wanted to propagate that culture, I would take a sample of it, put it on a new agar plate, and let it sit on the table or in an incubator and let it grow. If I wanted to stop growing, it's done, put it in the fridge. So freezing or refrigeration does not kill bacteria, but it does slow or stop their growth. So it's considered a microbiostatic. This is also why when you get done with food that you eat and you want to keep some leftovers, you put it in the fridge, because it prevents any bacteria from colonizing and growing out of control on the food. So that is why you put your food in the fridge or in the freezer. So outbreaks of food poisoning from frozen foods that are not adequately cooked, are a testament to this. So when you see outbreaks of E. coli or Salmonella or Shigella or Campylobacter, it's because there's something that went wrong in the process of growing or this food or harvesting the food, whatever food it is, to the point that it got to your table. There's something went wrong in the process of trying to eliminate microbial growth. All right, what about desiccation and lyophilization? Desiccation is drying something out. So if we remove water, it's going to dehydrate the cell and it's going to kill many microbes. So this is used in food preservation. Great example would be beef jerky. So beef jerky is made by taking meat and dehydrating it in a low-ish temperature oven, essentially, for a long period of time. So that would be an example of desiccation. Lyophilization is the combination of freezing and drying. And that's going to remove water, of course, because we're drying. And it's also going to expose it to freezing temperatures. And that combination of freezing and drying is going to prevent the cells from continuing to be able to divide. So it's going to halt growth. This is used very commonly in the lab to preserve cultures. In fact, I do have some in my freezer in my lab room that is a lyophilized culture. So they're freeze dried in these little tubes here, and then if I want to culture them, I would bring them to temperature and add water, and then after a couple of days I would be able to inoculate it onto an agar plate and have bacteria grow. So now we're going to move to our radiation methods. So we are done with heat. Now let's talk about radiation. Radiation is a wave. Radiation is energy emitted from atomic activities in the form of waves. Waves can come in various wavelengths. So to measure a wavelength, you would just take the length that exists from two consecutive points on a wave. So for example, we see a wave here, and we see the top of the wave on this one, and the top of the wave here. This would be two consecutive points on a wave, and if we measured that distance, it would be what wavelength is. Now, looking at our electromagnetic spectrum, which is this, and by the way, you don't need to have this memorized. I'm just trying to orient you in what a wave is and how it fits into what we're talking about. But we can see the electromagnetic spectrum here, which shows you all of the possible wavelengths, starting from over here, long waves, getting shorter and shorter and shorter to short waves. So radio waves are the longest, microwaves are a little shorter, infrared rays are a little shorter than that, visible light is a little bit shorter than the infrared. Then we see our UV light, X-rays, and gamma rays. The ones that's relevant for our discussion are these three. All right, so UV, which is ultraviolet, X-rays, and gamma rays. So let's start with ultraviolet rays. These are going to range from about 100 to 400 nanometers. It's not very penetrating. It passes readily through air, but not so much through liquids, and definitely poorly through solids. Thank God, because then if you went out in the sun, you would get a sunburn on the inside of you, which sounds very, very, very painful. But since it only really penetrates through the air very easily, it basically hits our skin, and that's where it stops. So UV radiation, not very penetrating. So the object has to be directly exposed to the UV rays for the effect to occur. So here you see some UV bulbs that are going to be used to help reduce bacterial growth in some kind of, it could be a culture, some kind of item they're going to place in there. Here you see one in a hospital room helping to decontaminate the room. And here I thought this was kind of cool. I inserted this in the PowerPoint because it just kind of because of the COVID, everything that has happened, and this is kind of something that I feel like resulted from COVID, because I don't think I've ever seen one of these prior. But you can see that someone's cell phone is in this little box, and it has UV lights that will help to eliminate microbes on their phone. Next, let's talk about gamma rays and X-rays. These two forms of radiation are ionizing. Backing track for just a second, UV rays were non-ionizing. Alright, so UV, non-ionizing. Gamma rays and X-rays are ionizing forms of radiation. And for that reason, it makes them very highly effective for sterilization. So this is really useful for things that are sensitive to heat or chemicals. Maybe the heat would, make it melt or make it unstable or make it unusable. Same thing with chemicals. If we can't use heat or chemicals, well, this is a great alternative to that, ionizing radiation, because it sterilizes it without the use of harsh heat or chemical exposure. So what occurs in this process are we can have items that are placed in machines that will expose it to ionizing radiation, and that will result in a sterilized product. And so here you see some images in research labs and industry, and here's a hospital lab example that is irradiating substances. And I'll elaborate on this one because I would guess it's probably the one you'll be most familiar with, or maybe even see in your field. But what this is a blood irradiator. So this would be found in your microbiology department likely, or depending on the organization of your hospital, blood bank. So the blood bank department is basically where hospitals will receive blood products, and they need to be sterilized, so they will put them in these irradiation machines before they are administered to a patient that needs a transfusion of, let's say, red blood cells or plasma, etc. So this is what that looks like, and we see the little red blood bags in there, and they're going to be irradiated. Okay, so that now we have covered heat and radiation. We're going to move over here, save chemicals for last, so let's do filtration next. So filtration is kind of like the colander or strainer in the microbial world. So everyone's seen one of these before, right? This is a colander, or some people call them a strainer, whatever you want to call it. And we see some strawberries, and if we want to wash the strawberries, we're going to apply water. You can see the water's dripping down, and that's going to allow all the dirt that may be on them or some of the microbes to pass through the holes of the strainer, but the strawberries will stay in the bowl. So that's basically what we're going to be referring to in filtration processes, just on a much smaller scale. So in filtration in the microbial world, we're going to have some kind of fluid that's going to be strained through a filter. And these filters are going to have openings, little tiny pores that are large enough for that fluid to pass through, but it's too small for the microbes to pass through. So if we look here, what this is showing you is some kind of liquid inside of this container, and we are wanting to filter it to make sure that the product, which would be below, is free of any kind of pathogens. So this filter here is shown very largely here. So we can see the filter in the background. These little rod things are bacteria, and you can see the pores of this filter are so small that the bacteria can't pass through, but the liquid can, the water can. So if we look at that from the side, you see the liquid in the container. Here would be the liquid that's or here would be the filter, the brown, this, and at the bottom this would be the filtered fluid in this Erlenmeyer flask. So again, we see the filter, it has little holes on it, and so it allows for water or the filtrate to pass through, but not bacteria, as we can see, too small. Or even viruses in some cases if they're small enough. So these pore sizes will allow for true sterilization as long as the pore size is small enough to where neither bacteria or viruses can pass through. So where are these used? These are used to prepare liquids, for example, that cannot withstand heat, like serum, blood products, vaccines, drugs, IV fluids, enzymes, and media that we grow bacteria on. So now we can also irradiate blood products as we've seen before, but sometimes depending on the usage we might use filtration mechanisms too. So for example, if you go to donate blood, typically they're going to separate the whole blood into blood components. So whenever you do that, you're separating the red blood cells, and you're separating the white blood cells, and you're separating the plasma, and so you can give a patient specific products. So typically whenever you have blood being taken from a patient, it'll go through some kind of filtration process at some point to separate those various items out prior to irradiation. This is an alternative method as well to pasteurization for milk or beer, even without altering flavor. It's used in water purification. Very simple example. Anybody have a Brita filter at the house? That's an example of this. HEPA filters are really common and used in hospital rooms to try to increase the sterility of the room because microbes cannot pass through them. Another example of physical agents that isn't in the chart but I wanted to mention really quickly is osmotic pressure. So if we add a ton of salt or sugar to some kind of food, it will cause the cells to dehydrate. So I believe y'all talked about this in A&P. I know you did if you took biology with me, but this relates to osmosis. As y'all hopefully recall, if we coat something with a large amount of salt, it's going to cause water to be drawn out of the cells. And as we've talked about before, when we dehydrate cells, it prevents them from growing. Or in this case, if it was a microbe, prevent it from making more of it, as an end result would cause the microbe to die. And so this is associated with pickling, smoking, and drying foods, and we've been doing that for centuries to preserve food. And curing meat by adding salt to the food has been done for a very, very long time. It's traced back to 3000 BC, as a matter of fact, long before refrigeration was a thing. So this is not a sterilizing technique, but it is a method to decontaminate things, such as these meat products here, so that they can be consumed at a later date without making us sick. Alright, so our final section we're going to discuss is our chemical control. So I'm going to jump back to that chart for just a second. So now we finished up filtration. Now we're going to talk about chemical agents. So our chemical agents can be liquids, gases, or solids. Some of them are going to be disinfectants, some are antiseptics, some are going to be sterilants that are going to sterilize substances, and preservatives. Many of them are going to be dissolved in water or alcohol. If it's a substance that's dissolved in water, it's considered an aqueous solution. And if it's dissolved in alcohol or an alcohol water mixture, it will be called a tincture, like Germ-X, for example. So these chemical agents have to have some, there's some criteria in chemical agents of microbial, microbiostatic or microbicidal agents. They have certain characteristics that are ideal. And this is a list of those characteristics. We want them to provide microbial control rapidly, even in low concentrations. So we want something that we're not going to have to use a lot of in order to kill microbes. We want it for a little to go a long way, basically. We want it to be soluble in either water or alcohol, as well as being able to provide long-term stability. For example, we just mentioned Germ-X. It's a alcohol water mixture with some other stuff. But if I bought a bottle of it today and I used it 5 years from now, it would still serve the same purpose. So it has long-term stability. We want the chemical agent to provide broad spectrum killing of microbes, meaning we want it to have the ability to kill a wide variety of microbial organisms, but at the same time not be toxic to humans or animals. We want it to be able to penetrate inanimate surfaces so that we can sustain long-term microbial side effects. We want it to have resistance to becoming inactivated. So we don't want it to a substance that's going to interact with other chemicals to make it not work. We don't want anything corrosive. We don't want anything that's going to cause staining. We want it to cause sanitization, though, and we want it to also potentially and ideally help with deodorizing properties. We want it to be affordable, and we want it to be widely available. So these are desirable qualities in any germicide. We can classify germicides into 3 levels: our high level, intermediate, and low level germicides. And these are going to be descriptive of how well they work, essentially. Our high level germicides kill endospores, and therefore they sterilize substances. Intermediate level germicides kill fungal but not bacterial spores. They also kill resistant pathogens and viruses. So germicides kill the intermediate level germicides kill fungal but not bacterial spores. It kills resistant pathogens and viruses. Our low-level germicides, on the other hand, eliminate only vegetative bacteria, fungal cells, and some viruses. So let's talk about some examples. And your book has pages on pages of examples, and I definitely do not expect you to know all of them. As you can see, there are highlighted points on this, and this is what the stuff I want you to know, just the highlighted things. So one example of a classification of chemical agents that are used as germicides are halogens. And halogens, for anybody that's taken maybe chemistry, might know what those are. They're specific to the 7th column, I believe it is, on the periodic table. But things like chlorine. Chlorine can kill endospores slowly and all other microbes. That's why it is used as an effective disinfectant for drinking water, or even your pool, for example, at home. If you have a pool, what do you add to it? Chlorine, because it disinfects the water. Sewage and wastewater is also disinfected using chlorine. Iodine is very commonly used in the healthcare fields. It can kill endospores and all other microbes, so it can be a sterilant. It's typically used as a topical antiseptic, which means it's used on the skin. So it is used very commonly to prepare the skin for surgery, to treat burns, etc. Next, some agents are oxidizing agents, and these are going to kill endospores and well as any other microbes, so they are very good at killing microorganisms. Some examples: hydrogen peroxide. Now, it's considered an antiseptic because in order to have it be used on living tissues, we need a lower concentration, only 3% or less, you'll find in the store. But if we use it as a sterilant, it would have to be at a much higher concentration, like 35%, which would be very, very irritating to the skin. You won't see that in your local drugstore. Next, aldehydes. These kill endospores and all other microbes. So far, all of the agents we've talked about can be used as sterilantes depending on the concentration. Excuse me. Okay, next, our gaseous agents include ethylene oxide. So this one's highlighted for a reason, you guys. This one's important. It can kill endospores, and it's a really excellent example of a gas that can be used for that process. So it's great for items that can't be autoclaved, that are sensitive to heat, for example, so that it can get sterilized without having to expose it to those high levels of heat. So ethylene oxide is oftentimes used to disinfect or sterilize plastic materials because we don't want them to melt in the autoclave. Also can be used for syringes, surgical supplies, medical devices that are prepackaged. Now, there is a downside to ethylene oxide. It's explosive, it can damage the lungs, and it is a carcinogen. So those are some down points there. But typically, this is going to be something that is used in somewhere that's going to package stuff that's sent to the hospital. You would never probably be exposed to it in the medical field, I don't think. But it's more or less something in the production of the products that are purchased by the hospital. Phenol. Some bacteria and viruses and fungi will die in presence of phenols. They are toxic, though. Next, chlorhexidine. This is going to kill most bacteria, viruses, and fungi. Alcohol. Same thing. It kills most of them. It's used commonly as a skin degerming agent to kill about 70 to 90 microbes on the skin. Again, so we're talking about an antiseptic. Typically, you'll find that in 70 to 95% concentrations in the store. Now, downside of alcohols is we're probably all aware that alcohol has a drying effect. It's readily evaporates very quickly compared to just water. So that fact that it evaporates relatively quickly means exposure time is going to be shorter, which means it's less effective as it evaporates. We have detergents. It'll kill some bacteria, viruses, and fungi. This is a low-level disinfection process in the clinical setting. And these can be used to clean restaurant utensils, dairy equipment surfaces, restrooms, etc. Because of we only need that low level of disinfection to make these clean enough, if you will, for use. Heavy metal compounds. Some bacteria, viruses, and fungi are susceptible. These are effective antiseptics again. However, downside is that microbes can develop resistance to them. And finally, acids and bases. Some bacteria and viruses and fungi, again, are their target. However, acids and bases are going to alter pH, and if we have large changes in pH, it can cause a substance or a chemical to become corrosive, which can be potentially not a good thing, especially if it's being exposed to living tissues like the skin. Alright, and finally, you do not need to memorize this. You don't need to memorize this chart. I'm just showing you some examples in your day-to-day life where you are coming in contact or using these various antimicrobial agents, some of which we've talked about today. So Lysol, it would be, the sanitizing wipes are technically a detergent. You can see the chemical agent that's involved is dimethyl benzyl ammonium chloride. Clorox disinfecting wipes. We see Tilex and Lysol mildew remover. Those are halogens because they contain chlorines, right? Sodium hypochlorite, sodium hypochlorites are in Lysol mildew remover as well. This one would be a detergent. We have Renew contact lens solution, contains chlorhexidine. We have Scope mouthwash, contains ethanol, which is an alcohol. Hand sanitizer has alcohol and sometimes a detergent as well. Eye drops are halogens. They're going to have sodium chloride in them, which has a chlorine atom, which is why it's considered a halogen. Alright, so that is it. That summarizes Chapter 9. So I will talk to y'all again sometime soon for Chapter 10.